When catastrophic flooding hits, we usually look at rainfall totals, inches, feet, records broken. But what if the most important number comes before the rain ever starts? In 2024 and 2025, floods across the United States and around the world unfolded with terrifying speed. Overwhelming communities, stranding families, and shattering records that once seemed untouchable. A new investigation by the Washington Post suggests the real story isn't happening on the ground. It's happening way above our heads. Using a powerful metric called integrated vapor transport, the reporting reveals how massive flows of atmospheric moisture are intensifying for certain parts of the globe, creating hotspots that turn storms into deadly floods. Today we're going off the radar to understand how these hidden currents are shaping our weather, our communities, and our future. I'm meteorologist Emily Gracey, and you're listening to Off the Radar, a production of the National Weather Desk. On the show, we dig deep into topics about weather, climate, the ocean, space, and much more. Our goal is to help you better understand the weather and to love it as much as we do. Floods can be sudden, devastating, and hard to recover from. But what if the real story isn't just the rain that falls, but the moisture in the sky that never used to be there? In November, the Washington Post published an investigation titled Deadly Rivers in the Sky, revealing how rising global temperatures have supercharged the movement of moisture through Earth's atmosphere. Using state-of-the-art data, including a metric called integrated vapor transport, or IVT, the reporting shows where moisture flows have intensified the most and why these areas now face grave risks of extreme rainfall and flooding. Regions with higher IVT are not only getting wetter, they're getting hit harder and more often. To help us unpack this complex but crucial topic, I talked to someone who spent a year digging into the data and the stories behind it. Washington Post meteorologist Ben Noll. Ben has been at the intersection of weather, climate, and data visualization, helping translate complex meteorological science into real-world understanding. In fact, I highly recommend you follow him on X. His weather content is not only informative, but the graphics make it so easy to understand. In this episode, we'll explore what IVT is, how climate change is altering these rivers in the sky, and what that means for communities around the world. All right, Ben Noll, this is some cool stuff you're doing here. I'm excited to pick your brain about what came out here in the past couple of months with the Washington Post article. Lots to dig into, but I want to start with you and your background. You know, we were just kind of talking before I hit record about your background. You live in New Zealand. This is wild.
Yeah. Thanks so much for having me, Emily. Yeah, this is, coming from a place in the future. We're about 18 hours ahead of the Eastern United States. So we know all that's going to happen with weather. No, I'm just joking.
It's a meteorologist's dream.
Yeah. Don't have that magic book like they had and Biff had in Back to the Future, to predict the spring for weather. But no, so I'm based in New Zealand, near Auckland, north of Auckland, kind of on the edge of the subtropics in the southern hemisphere. The day we're recording is actually the summer solstice, so it's our longest day, 14 hours and change. So, quite a bit of sunshine. And for people that may not know so much about New Zealand, the climate here is pretty mild. We're surrounded by the Pacific Ocean to the east, the Tasman Sea to the west. So we have, pretty flat temperatures here in Auckland. The average high in winter is in the upper 50s and in the summer, maybe in the mid to upper 70s. So it's pretty even throughout the year. We don't go below freezing except maybe once or twice a year. So yeah, pretty pleasant place to live. I would say overall.
Obviously, you sound American, though, so you're not from there. And you work for the Washington Post. So this is interesting. You're working from quite a distance. What do you do for the Washington Post?
Yeah, so quick background. I'm from New York originally, went to the State University of New York at Oswego, which is on Lake Ontario. So we saw these amazing lake effect snow events. So the laboratory was like right there at the school. Worked at AccuWeather for a couple of years in State College near Penn State there in Pennsylvania. And then, over to New Zealand in 2016, where I've been now, almost for a decade. Worked for the government as a meteorologist for about 9 years. And now with the Post, do global weather and climate coverage. So depending on what is happening in the world, where it's happening, cover that and try to bring kind of some, interesting data angles to some of the weather that we're seeing. We're kind of in this very data rich age where there's so much available, whether it's weather forecasting models or historical data, and trying to contextualize that for, the public audience, and the post, readers.
Cool. And I want to pick your brain about data visualization here in a little bit, but let's talk about this article or investigation. First of all, I think it's really interesting when this came out in November, investigation by the Washington Post about weather and climate. This is kind of mind-blowing to me. I'm used to seeing like an investigation that's a little bit more criminal in nature, I guess. So to see something about climate, it's very fascinating. Can you tell me how this started? Like what prompted this particular investigation?
Yeah, so the name of the series that launched is called Floods Above. And what it basically looks into is the amount of water vapor, this invisible gas that is, above us all and contributing to the rainfall events, the rain that falls onto the ground. And there's been this kind of, I think, focus in the weather world on a warming climate and how temperatures are increasing, but maybe a little bit less so on how some of the other variables are increasing, such as humidity or the amount of vapor or fuel for the storms that we see are experiencing in the atmosphere. So what we wanted to do was kind of uncover some of those new layers and dig a little bit deeper into this fuel aspect. And what we looked at was a metric called integrated vapor transport, kind of this nerdy term, IVT for short. But basically what it does is describes the amount of moisture flowing through the atmosphere, its speed, its direction, and its magnitude. In a context of like a weather forecaster, we often look at the amount of moisture in the atmosphere as a way to kind of understand how intense a storm may be. We call it precipitable water, which is kind of this measure of the total amount of moisture in the atmosphere from the ground all the way up to the top. What IVT does is it kind of takes that variable, the magnitude, but it also describes how it is moving around. And it can be very helpful to understand where kind of moisture sources are. So is this moisture plume, let's say with Hurricane Helene, where did that originate from? And how can we use that information to understand how intense the rain that is going to fall out of those clouds may be when it gets there? So that's kind of what IVT does. And I think, in the community, forecasters, meteorologists probably quite familiar with this moisture, but more so on a weather time scale. What this project did is actually went back several decades to kind of understand how this metric has changed. And we can use that information. What we did was we used that information to kind of pinpoint these hotspots around the planet to understand where that change is happening the most. And we paired that up with actual rainfall data, because one thing to have a lot of moisture in the air, but you need something to wring it out and actually cause rain, precipitation to reach the ground. So we kind of paired those two things up, the moisture and where it is contributing to frequent heavy rainfall events to identify, on the planet, some of these global hotspots.
Okay. Let's go back to kind of how you gathered the data. What tools did you use? How do you measure IVT?
Yeah. So fortunately, in the year 2025, the amount of weather data and climate data that is available is almost endless. So one of our key data sets was the ERA5 atmospheric reanalysis. So this tool that allows from ECMWF, the European Center for Medium Range Weather Forecasting, goes back to 1940. And it allows us to kind of understand, it gives us this historical view of the world for all sorts of different weather variables. Now, what goes into that data is a whole bunch of different sources. So back in the 1940s, when there was much fewer weather stations around, that was before the satellite era, there's less input data. But as time went on and there was, more dense data available, be it from satellites, be it from these microwave sensors, be it from weather stations, ships, aircraft, weather balloons, the list goes on. What you saw is an increase in the amount of data available through time. And now, in, of course, 2020s, tons of different data kind of goes into creating this baseline for are real time and historical weather conditions that we can kind of look at. So that was a key data source for our work. And we also looked at something called the MSWEP, which is a rainfall data set. I think it stands for multi-source weighted ensemble precipitation. You can check me on that. That's kind of pulled that one out. I'm not 100% sure. I think that's it. But what that does is it gives us kind of this real-time assessment for daily rainfall around the planet based on a range of input. So you have stations, you have satellites, and other different tools that can kind of fill in some gaps where there are not weather stations, because that's a key thing. There's not a weather station on every corner of every street. So we need to use these remote sensing tools, radar and satellites, to kind of help to fill in some of those gaps. So in total, we downloaded about like 3 terabytes of data for this project. So it was a pretty big data lift, I would say. But at the end, we parsed that down into little bite-sized pieces and something that could create a really compelling story.
What was the time period that you looked at?
We looked at the full 1940 to present period. But as part of the research and part of the investigation, we reached out to a whole host of experts within this field of water vapor, and especially water vapor trends in the atmosphere. One person that we talked to was Dr. Tevin Trenberth. He used to be the chief scientist at NCAR for back into the early 2020s, and he retired. But he suggested, he's an expert in this kind of water vapor trend space. He suggested focusing more on the period from the early 1990s, about 1992 to present. And that's because that is when kind of the best water vapor data in that historical data set that we used is. So there are some kind of, the further back you go, the more kind of discontinuities there are. But as the tools that measure that water vapor got better, there was a period in about 1992 when that dramatically improved. But even if you look at that relatively short time period, you actually see some pretty steep trends. So I think, there's this idea, well, it's a kind of a short time period, but the way I look at that is, well, yes, it's a short time period, but there are actually some pretty stark trends and change within that relatively short period. And we also, again, look back to 1940. And if you go further back, you see even steeper trends. But yeah, we focused on kind of this modern 33-ish year period.
In the way that climate scientists are looking at like really old information on temperature, in tree rings or in ice cores, is there a way to like draw that sort of data when it comes to IVT? Is there any way to look before the 1940s?
Yeah, look, I think the further back you go, like you're trying to fill in these relatively sparse observations with models, with models that are going to kind of interpolate between those sparse observations in the atmosphere. So I think that the further back you go, the more challenging it gets. I mean, I suppose you could probably look at those same things like in a paleoclimate space, like the tree rings, not my expertise, but you could also probably pick out periods of drought and heavy rainfall using that same technique. But of course, it's not going to necessarily give you, an IVT measurement. But the amazing thing is now, and as well into the future generations, I think we kind of try to create like a little bit of a baseline for someone in the say 5, 10, 20 years down the line when, AI is running the world. I don't know, but like, this investigation can spur some additional thinking about, how it could be improved. What are some of the new things that we have now? And, you can basically rerun it every single year to see how, 2025 is say tracking versus that historical period.
Okay. You brought up AI. Was there any talk of using AI, or did you use AI at all in this? It seems like it would be a great tool for this sort of study.
Yeah, look, I think for any forecaster meteorologist that does data analysis, AI is like a huge asset or a brand new tool on the tool belt to help to either expedite or improve those analysis. Whether that's through, plotting data, whether that's through generating statistics. I grew up as someone who learned how to code in undergrad, Python, and I've been doing it now for kind of on the job for about a decade, maybe a little bit more than that. So what AI has allowed me to do is take some of these historical plotting, coding routines that I have, and then basically refactor them, basically improve them. So they're, they can run faster, be smoother, generate insights that might take me a really long time if I try to code up by hand. Now that can happen in seconds. So I think from an analysis point of view, it certainly influenced, some of the work that we did. And it's hard to imagine without having that tool, just how long it may have taken to do a similar analysis. So, I think it certainly helps, I think, in that technical realm to generate these insights faster than ever.
Okay, so tell me about the process and the time period. How long did this take? What does your team look like? Who worked on what? The end result was very pretty too. So I'm guessing this is kind of a long-term project.
Yeah, so it all started in DC. I was there in November 2024 and had a meeting with some colleagues and editors, and I just kind of floated this idea out there. And I called it initially global moistening, which didn't really make the final cut as the name, but that is the overarching concept underneath. I don't know. That probably wouldn't make for a great headline, whatever. But I thought it was, it was a fun name and a fun way to look back at the kind of the seed here, right? So from that point forward, it was like a year-long effort. And look, the Post has, for people that might not be familiar, there's a team of about 30 odd people on the climate team, journalists, data visualization, editors that really care about getting, the best information out there. And I would say that for the whole team. It's a really neat place to work. And I kind of planted this seed with this data analysis, and I liked how all of each of my colleagues kind of took it in a different direction, because there was this one initial story and idea, but we had people that traveled to India to look at how changes there are affecting dams. We had someone travel to Oman to understand how rainfall is changing in the desert. We did something about New York City subways and how in New York City we're seeing year after year these like higher rainfall, hourly rates being reached, and how that's affecting, the subway system. So, it was a long effort where, I have this little, I'm based in New Zealand. I've got, a decent laptop, and I would literally let the thing run over the weekend. And I'd like download like one file at a time, and I would have the script like take out the little bits of information that I needed, process it in a certain way, and then save it. And because, I only have so much space on the laptop, I'd have to like delete some of the older files in order to kind of allow this process to accumulate all of the years that we needed to do it. So, you got to get kind of creative. If you have like a supercomputer, then, that's probably not a big issue. You can have like endless storage. And we all work in different time zones. So we've got people in Europe and England, someone in San Juan, in Puerto Rico. So we kind of all worked together and all had our piece of that puzzle that we were trying to, put together. So a true team effort. Exchanging data through the cloud. Here's, I need this. Someone you message you, that you send it to them, and then they take it and they, maybe spin that up into this really beautiful visualization that you see in the end piece. But when you read this story, or really any story that comes out of the Post, and you see these really kind of amazing visuals, I think for the average person, it may be difficult to understand just how much actually went into getting to that final piece that is published.
Okay, let's dig into the science a little bit more and these specific hotspots that you're talking about. Can you talk individually about some of them, like especially any that may have surprised you? Like, oh my gosh, I had no idea about this spot on the globe that's being impacted this much.
Yeah, so the hotspots, as I look at a map on my screen here of all the little areas around the globe, I think the one key message is that integrated vapor transport since the early 1990s has increased across over 80% of the planet. So this concept is affecting many different places, but not necessarily equally. Some places that are very dry, like let's say the Sahara Desert, that may only mean, small changes in the amount of rainfall. But for places that are really wet, that are facing, frequent atmospheric rivers, frequent plumes of moisture in the sky that originate from great distances, it can mean quite a bit. So we kind of try to distinguish, signal from the noise. And when we looked at those signals for where this phenomenon is driving, more heavy rainfall, we find the east coast of the U.S., whether it's Florida or Maine, right up into, in fact, eastern North America, I should say, into Newfoundland and Labrador. So this area is one really key zone, and obviously hugely populated. Some interesting things, I think, behind the eastern hotspot is not just this kind of underlying change in moisture levels, this increase, but also IVT gives us an insight into how circulation patterns, so areas of high and low pressure, are changing to fuel more winds coming from a certain direction. And if we look at that circulation angle for the eastern U.S., what we find is kind of a change to a prevailing flow pattern that's more from the southwest. And of course, to the southwest of this area is a very warm body of water, the Gulf of Mexico, as well as the Caribbean. So you're getting kind of more moisture flows from that zone that is boosting kind of this, it's another layer on top of that underlying increase. So you have kind of this, there may be the human influence, which is, warmer temperatures driving more moisture in the air. And then you probably have some natural variability on top of that is actually enhancing things more. So the eastern U.S. is a pretty big hotspot. Western Europe, we've heard a lot out of flooding out of Spain recently, pretty much the entire country, Portugal. That is also a hotspot. So frequent flows kind of around the northern side of the Bermuda High across the Atlantic Ocean, reaching the land there first, and wringing out quite a bit of moisture. And Spain's an interesting one because, if you look back at the Valencia floods and you kind of look to where some of the moisture for that event in late 2024 originated, you kind of actually see some of that coming off of Africa, which was toward the tail end of their monsoon. And in that part of Central Africa there, that is also a hot spot. So these areas that are relatively dry are actually becoming moister in the atmosphere. And some of that actually may have these distant influences across hundreds of miles, maybe even affecting places like Southern Europe. And the list goes on, I would say, also pointing out Southern Asia, South Asia, India, Nepal, Bangladesh, the Philippines is a really big one as well. The West Pacific, the oceans there are really warming up. We've seen this trend over the last 4 decades to more La Nina events, which is kind of interesting. And whether that continues or not, probably a totally separate conversation. But what it has done is influenced basically higher moisture levels. So typhoons, the monsoon there, basically having more fuel in the atmosphere that can turn into more rain on the ground, and obviously a very vulnerable place, very densely populated. The Philippines is, so more rain in a place like that is not, necessarily a good thing. But I should say, what is interesting is that there may be places on the planet where having more rain isn't necessarily a bad thing. It kind of forces us to rethink about, as patterns change, how things may evolve in terms of farming practices, different temperature bands, depending on what hemisphere you're in, moving north or south, and how the rainfall will change with that. So it's kind of, I think it also informs some of this like adaptation piece, how we kind of shift our ways with a warming and moistening world.
It's interesting what you're saying about the knowing where the moisture is coming from, like originates when you talked about like Helene or the flooding in Valencia. Does this make a difference when it comes to long-term forecasts? Like, are long-term forecasts going to get better knowing like if this is originating here in 10 to 14 days, it might be here? Does this information going into computer models make a difference?
Yeah, absolutely. I think it does. I mean, I think, our ability to track these moisture plumes has, become much more accurate with time. So as weather models have improved, you can predict atmospheric rivers, week to 2 weeks into the future sometimes. and some Scripps out of California is doing really good work with that, kind of along the west coast of the U.S. They've got this atmospheric river ranking system from category 1 to 5. And what I would say is kind of an analysis like this. I think as a forecaster, we're kind of very much maybe focused on our region that we're, let's say, covering. But part of the bigger picture is, if you're in, let's say, the Carolinas, for instance, continue with the Helene example, to kind of understand that, this is part of a long-term trend where I live and where I'm forecasting for, and kind of trying to integrate some of that information into that forecast delivery process. So, even if it's a weather story that you're doing, there's a big storm hitting, it's got a lot of moisture with it, kind of adding that additional piece of context. And this is a place where these things are becoming more common with time. That is kind of I think an important piece of the puzzle, as we go into the future for meteorologists to kind of consider within their communications. And we also heard from some government agencies that, this is kind of a new data layer that is really interesting for them, especially if they are in one of these, let's say, call them global hotspots. And if they can overlay that with some of their other more local data sets that they may have, whether that's, population or farming areas or some other piece of data that can kind of, when combined with this information, can generate more insights.
Something I want to address that I don't think we talked about right off the top was the relationship between global temperatures and IVT.
In this space, I think there's this kind of often cited metric. So 1 degree Celsius leads to the moisture holding capacity of the atmosphere to increase by 7%. So it's about just under 2 degrees Fahrenheit, 7%. And that's called the Clausius-Clapeyron relation. So it's a bit nerdy.
I haven't heard that term in a long time.
Yeah. It's taking back, the undergrad days.
Yeah.
But a warmer atmosphere has the ability to hold more water vapor. That's kind of what it boils down to. It's a physical relationship. So, it's something that was established, a long time ago. And it, tells us that as we go through time and as temperatures continue to warm, that we should see increasing amounts of vapor in the atmosphere. And again, that doesn't necessarily mean that all of that vapor is going to be squeezed out into rain. But I think the analogy I would use is, and I've heard this, I think, from Daniel Swain, a climate scientist in California. He calls it the expanding atmospheric sponge. So if you think of the atmosphere like a sponge, that sponge basically can expand and hold more vapor the warmer an atmosphere becomes. So I kind of think of this thermal expansion in my head, and the sponge kind of becoming fatter and more loaded with water, and that's the sky. And then if you think of kind of wringing that sponge out, well, if there's a little bit of moisture, it's only going to drip down. But if there's a whole bunch, well, then there's going to be a big pile of water on your table in front of you. So expanding atmospheric sponge, I think, is kind of the analogy I would go with there.
Are the triggers the same? The squeezing, has that changed, or is it just a matter of if it does or doesn't, then it could be this big event?
Yeah, it's a good question. I mean, you think of the triggers from like a meteorological perspective, you need to get the air to rise somehow. And when the air rises, it cools, condenses into clouds, and eventually, if there's enough moisture, those clouds are going to drop precipitation. So what are the things that we need to generate that process? Well, that can be like a front, that can be a cold front, that can be the moisture, a big moisture plume kind of colliding with a mountain range, and that causes the air to rise. That's orographic lift. It can be individual thunderstorm cells, convection, that harness very local levels of moisture, like we saw with the Texas floods, which I should say also had record high levels of moisture associated with that system. So I would say that, while the triggers themselves are different, this phenomenon can kind of touch all of those different triggers in different ways.
Yeah.
So are the triggers necessarily changing? Maybe not so much. But what is changing is kind kind of the level of fuel that some of those systems may have at their disposal. So, I think there's, more to be done, especially in that circulation space, and kind of disentangling how much of this change is related to the changes in circulation wind flows versus how much of the change is related to this long-term warming trend, and the increase in moisture in the atmosphere. And there are different ways to get at that. I would say that's probably more of like a PhD style thing, than, say something that's going to come out of the Post, but it's absolutely something that we kind of considered in that process. But, to make it kind of accessible, some of those really dense topics, I think we've left for another time.
Okay, so I want to talk about that too, because a lot of times, I'm finding stories or doing podcasts because maybe I read an article in a newspaper that was discussing an academic study that was done or a paper that was written in a journal, but the original source is never been a newspaper before. I've never reached out to a newspaper and talked to them directly about their study. So I want to know, is this new and unique? And I'm very curious about this process and if this is going to be the way of the future too, especially as we're seeing some government entities and research groups being dismantled or shut down. Do you think that we need more newspaper research projects like this?
Yeah, it's an interesting question. I think in some respects, kind of as you say, I guess it's kind of let's just say this, it's unusual to see maybe something so data rich, data dense, meteorologically rigorous. We had people, renowned world researchers in this area kind of review our work, provide comment, iterative process back and forth, to really try and make this, as buttoned up and as strong as we could make it. The media landscape is changing, and obviously the research landscape and the forecasting, it's all kind of changing quite rapidly. So, it's an interesting wrinkle, I guess. The Post has a really strong reputation of good meteorological content from the Capital Weather Gang, run by Jason for a really long time. He's still doing that for the DC and Mid-Atlantic side of things. And I'm, kind of on this national side doing the weather for them. But, I think it's an opportunity, to try something a little bit different. And working at the Post, that's what I found is like trying new things, not being shy, really strong belief in good science in this case. So, I do think maybe it's a kind of this model, maybe in some respects for the future. Of course, IVT has been studied. If you look around the internet, there are some really good papers. But, I may be biased, but I think some of the, the graphics that came out of our story are probably the coolest IVT moisture transport animations that are out there. And yeah, speaks to the kind of dedication that it takes and time that it takes to do something like this.
Well, the benefit too is that it speaks to the public. Like a journal is not going to speak to the public. You brought this to the masses. This is understandable to the general public. And I guess that's a huge draw of a newspaper being in charge of this too, is the ability to communicate well, the social science aspect of this becoming information for everybody. So can you tell me about that part and the data visualization and what went into that and what people will see if they read this article? It's not your typical old-timey newspaper article. This is a data-rich, visual-rich, very interesting and easy to digest information.
Yeah. So, that process, it takes months, it took a year basically to kind of fine tune, things that are as simple as, are we going to use the phrase integrated vapor transport in this story or not? These are things that are basically discussed, on the team level. How can we make this information the most accessible that it can be when it has so much kind of science and technical bits behind it? So there's, meetings every single week for a full year discussing some of that finer detail information. That's, discussed at of course, journalists, we can take a good stab at writing a story, but, there's going to be, guidance and mentorship leadership from editors who are going to actually, maybe it's better to kind of phrase it like this because more people will understand that type of phrasing. So just to try to help people understand that process, this is, not something that kind of happens overnight. It's really like, really think about that, sleep on it for a whole weekend about how you may want to kind of phrase a certain paragraph, to make it so that it is, it's more understandable. So that communication aspect, again, is huge, as you say, comparing it to a journal where you're going to get, lots of really, really rich information, but maybe not quite presented in a way that everyone can understand. And of course, another way to do that, in addition to words, is as you asked and said, is the visuals. So the Post has several really amazing, visual kind of journalists that, what I can do is generate data. And in the meteorological world, we often use, so there's a couple different key data types. One is called NetCDF. Another one is called GRIB. These are kind of multi-dimensional data because the atmosphere, has multiple dimensions from the ground all the way up. So you have these different height levels, you have different variables, you have different time steps, so multiple dimensions, and turning that using tools, either Python or GIS type of tools, into these incredible animations or static images. So you think of this a tiny little data piece that was once kind of sitting on a supercomputer in Italy, where the ECMWF built, designed their new one a couple of years ago, to the front page of the Washington Post, which is where the story ended up. And to go from end to end there, that is a huge, huge amount of work. Credit to, I think, the many dedicated people that can help to make that happen, but also to the community, because, ultimately, what we're seeing as we go through time here, and people are on their phones, they're consuming information in very different ways, right? So, are you really scrolling through a research article on your phone? Well, some people might, but would you rather see this incredible animation on TikTok or Instagram? Which one is going to resonate more with you?
Mm-hmm. Yep. People want the information. So got to get it to them. Okay. Yeah. So what's next? Can you share anything that you're working on now? Any new projects in the works?
There's no shortage of data out there. So there's so much, I think, left to explore, to uncover, so I haven't, necessarily come up with some magical idea for 2026, but I think there's so much left to be explored. Why are these, moisture plumes becoming stronger in certain areas? What is the fundamental driving force? We know climate change is increasing the moisture levels, but what are some of the other things that we can uncover about these trends? Humidity levels. We've felt, if you were in the US this summer, there was some ridiculous humidity. So how is the humidity that we're feeling impacting different parts of the world? And, I think that's another really kind of interesting sidebar from this. And then there's the oceans as well. The big moisture source for a lot of these long vapor plumes, transient vapor plumes, is the ocean. So the ocean, is really that underlying driver. And, they say, we know more about, the surface of Mars than we do the bottom of the ocean. So what can we uncover there? So I don't know exactly what is next, but that's kind of the fun of it. Something will come up. I'll be out jogging one day and, I'll be, oh, that's actually what I want to do. And sometimes those ideas, they don't come up when you're, trying to actually think about them. They come
Never.
up in these random situations, right?
Middle of the night.
Yep.
Well, Ben, thank you so much for your time. I appreciate it.
Yeah, thanks so much for having me, Emily. Take care.
Off the Radar is a production of the National Weather Desk. Make sure you're following the show on Apple Podcasts, Spotify, or wherever you listen to podcasts. New episodes publish every Tuesday. I would love to hear from you, so please reach out on social media. You can find me at Emily Gracey Meteorologist on Facebook and X. You can also follow Off the Radar on Instagram. I want to know what you like and what you don't like, and what you want to hear more of on the podcast this year. Thanks to Ben Noll from the Washington Post for sharing his research today. Make sure you check out his Deadly Rivers in the Sky article, which was published in November of 2025. Also, follow Ben on social media to get great weather updates. Even though he lives in New Zealand, he has a great eye on U.S. weather. Thanks to the National Weather Desk and Sinclair Broadcast Group for their ongoing support of the podcast, and to Brian Petrus for his help with today's episode. I'm meteorologist Emily Gracey. Make it a great day.